Hi everyone, welcome back. In this video, we will discuss how to calculate the pH of a solution that has a mixture of acids. Okay, let's look at the first scenario. What happens if we have a strong acid and a weak acid mixed together? Okay, well, a good example would be hydrochloric acid and formic acid. So the first thing you ask yourself, what's in my beaker then? If I have these two acids in solution. Well, let's write down the equations. We know that hydrochloric acid is a strong acid. So in the presence of an aqueous solution, it dissociates completely into the hydronium ion, the conjugate acid of water, and the conjugate base of hydrochloric acid, which is that chloride anion. So that's happening in your beaker. In addition, you also have formic acid dissociating, not fully, only partially, since it's a weak acid. So therefore, use the double-headed arrow. It is also donating protons in solution in the form of hydronium ions. It's the conjugate acid of water. And then the conjugate base of formic acid, which is formate, has a -1 formal charge. So that's also happening in your beaker, as well as the autoionization of water. Remember, water is amphoteric. It can act as an acid or a base. And so this is also occurring in your beaker. And we know that to calculate the pH of a solution, it's negative log of the hydronium ion concentration. So we've just shown here, if we have a mixture of hydrochloric acid and formic acid in an aqueous solution, we have these three possibilities of sources for hydronium ions in solution to calculate our pH. That's a lot, huh? Well, let's talk about HCl. We know that HCl, since it's a strong acid, produces the hydronium ion concentration of 0.1 molar. Since it completely dissociates, so we started with 0.1 molar HCl, therefore we for sure have 0.1 molar of hydronium ions in solution after it dissociates completely. And according to the Le Chatelier's principle, the formation of the hydronium ions by the strong acid causes the weak acid and water to dissociate less. So imagine your beaker, right? This HCl is a strong acid. It's completely dissociating. We have all these hydronium ions in solution. And so therefore, if you look at the equilibrium of the formic acid, we're increasing the concentration of the hydronium ions, which shifts the equilibrium based on Le Chatelier's principle to the left, right? It suppresses the equilibrium for the formic acid. It does the same for the autoionization of water. Let's see an example of this in the race table form so we can prove to ourselves that when you mix a strong acid and a weak acid, that the strong acid dissociation just completely suppresses the weak acid equilibrium as well as the autoionization of water from producing a significant amount of hydronium ions to affect the pH. Let's prove it to ourselves. All right, so we know that formic acid's in solution. I'm just writing down the equation, the hydronium ion and the formate anion. Now, initially in our beaker, we had put in 0.1 molar of formic acid, But now we also have an initial concentration of hydronium ions from the strong acid as well. And so this is also 0.1 molar. And that's from the HCl. Now, formic acid changes by -1x over time. It's decreasing. Hydronium ions are increasing them by +1x, and the formate +1x. So at equilibrium, we have 0.10 minus x, 0.10 plus x, and x here. So we want to solve for x because eventually we would like to see what the hydronium ion concentration is at equilibrium. And so remember, we're going to use the equilibrium constant expression, products over reactants. So we have the hydronium ion concentration times the formate over the concentration of our weak acid, formic acid. And we plug in the equilibrium little algebra equations. And you would look up the Ka value, or it would be provided for you on an assessment for formic acid, which is 1.8 times 10 to the -4th. Now, let's assume x is small enough to ignore to help us out with the math of it. So if that's the case, we can ignore a -x and a +x, because basically what we're saying is it's such a tiny amount, it's almost zero, it's not significant. And when we do that, we see that and solve for x is equal to 1.8 times 10 to the -4th. Now let's check to see if this is a valid assumption. So we have 1.8 times 10 to the -4th. Remember, you have to divide by the initial concentration, 0.1 molar times 100%. And this is equal to 0.18%. So yes, x is definitely less than 5% of the initial concentration. It is small enough to ignore. So therefore, the hydronium ion concentration at equilibrium from that Rice table is equal to 0.10 plus x, which is 1.8 times 10 to the -4th. And so that concentration then at equilibrium would be 0.10018 molar. And before even looking at the formic acid, we said that the 0.1 molar hydrochloric acid, 0.1 molar hydrochloric acid solution already produced 0.1 molar hydronium ions in solution. And so this did not add too much from the formic acid equilibrium. It's a pretty small amount here. So therefore, this is such a small amount that has been added, right? That little amount there. Therefore, we can say that the concentration of the hydronium ions is dominantly from the strong acid. Okay. In addition, the autoionization of water has a kW of 1 times 10 to the -14th. It's so small. So it is even smaller. So we can ignore it too. Okay, so in summary, if you have a strong acid mixed with a weak acid, then you can calculate the pH of the solution from the concentration of the hydronium ions that are produced by the strong acid only. Le Chatelier's principle is helping us in that favor to suppress the equilibrium of the weak acid as well as the auto-ionization of water. All right, well, what happens if you mix two weak acids together? Well, we'll look at the Ka values, and if the Ka values of the two weak acids are sufficiently different, and what I mean by that is that it differs more than several hundred, then as long as the concentrations are pretty similar in magnitude, we can assume the weaker acid will not make a significant contribution of hydronium ions. So basically what we're saying is that even if there's two weak acids, if one of the acids is stronger than the other relatively, then we can just calculate the pH based on the stronger of the two acids. Let's work an example together. Let's find the pH of a solution that contains 0.095 molar hydrofluoric acid and 0.225 molar phenol. All right, so first things first, we just have to look up the Ka values. The Ka value of hydrofluoric acid at 25 degrees Celsius is 6.8 times 10 to the negative fourth. Now be careful, in the textbook that we're using, they have that Ka value within the context of the chapter you're studying right now. However, in the appendix, they've written it as 3.5 times 10 to the negative fourth. Now don't worry, for an assessment, I would provide the Ka value, so it'll be quite obvious which one you should use. But technically, for hydrofluoric acid, it should be 6.8 times 10 to the negative fourth. And the Ka for phenol is equal to 1.3 times 10 to the negative 10th. All right, so we can see that they differ by several orders of magnitude. Which one is the stronger of these two acids? Yes, definitely HF here, right? The larger the Ka, the stronger the acid. So since HF is the stronger acid relative, it's still a weak acid, but just relative to phenol, then we will calculate the pH based on hydrofluoric acid. All right, it's a weak acid, so let's do our rice table. So we have HF in an aqueous solution produces the conjugate base, which is fluoride, plus the conjugate acid of water, which accepts the proton, right? It's the base right now. And so that's the hydronium ion. So always talk yourself through it. This is the acid, it donates a proton, so that's the reason why we end up with this conjugate base fluoride with the -1 charge. Water's acting as a base in this case here, and so the conjugate acid of water is the hydronium ion. It doesn't matter which order you write the products, by the way. All right, so then initially what we put into our beaker is 0.095 molar hydrofluoric acid. We don't have anything of fluoride in there or a significant amount of hydronium ions in there. It changes by -1x over time and then +1x for the products, increasing. And so at equilibrium, hydrofluoric acid will be 0.095 minus x. And then fluoride will be 0 plus 1x, which is x. and same for the hydronium ion. Now we're asked to calculate the pH of the solution, so we're mainly concerned about the hydronium ion concentration at equilibrium. We just want to solve for X here. So let's go ahead and set up the Ka expression to help us to do that. So products over reactants. And that's equal to X squared over 0.095 minus X is equal to 6.8 times 10 to the negative fourth. Now we can go ahead and try our trick out and see if X is small enough to ignore, so just crossing out minus X. And when you solve for X, you would get 0.008037 divide by the initial concentration times 100% to see if X is less than 5% of the initial, and unfortunately it is not, so that's not going to work. So therefore we're going to have to use the quadratic equation to solve for X here. And so I'm going to write this down again. X squared over 0.095 minus X is equal to 6.8 times 10 to the negative fourth. Make sure you get comfortable converting this equation into the quadratic form of ax squared plus bx plus c is equal to 0. And when you do, you should get x squared plus 6.8 times 10 to the negative fourth x minus 6.46 times 10 to the negative fifth is equal to 0. And then that way you can solve for x. You'll get two solutions. It's negative b plus or minus b squared minus 4ac over 2a. So it should look like this. Negative 6.8 times 10 to the negative fourth plus or minus the square root of b squared minus 4 times a, which is 1, times c, negative 6.46 times 10 to the negative fifth, over 2 times a. You'll get two solutions, but one will be bogus because it gives you a negative concentration at equilibrium. So one was x is equal to negative 0.0083846, or x is equal to 0.0077246. So if we look at these two answers, which one is the one that's not going to work for us? That's correct. The first solution is not valid because that would mean that we would have a negative concentration of the hydronium ions as well as that fluoride, so definitely not going to happen here. So therefore, x is equal to 0.0077246. This is also equal to our hydronium ion concentration. At equilibrium. Remember, the question asked us for the pH, and the pH is the negative log of the hydronium ion concentration, so 0.0077246, and the final answer you should get is 2.11. Always ask yourself, what's in my beaker? And what's in your beaker are a couple of weak acids, and therefore you do expect an acidic solution and a pH less than 7, and indeed that worked out in this case here, right? So always kind of double check your work, ensure that it makes sense so that there was no algebra or calculator errors. So in summary, when you have a mixture of weak acids, check out their Ka values. The one that has going to have a significantly larger Ka is the acid you will use to calculate the pH of the solution. So you'll need to calculate the hydronium ion concentration at equilibrium in order to solve for the pH. Thank you all for watching, and I'll see you next time.